I'm Ryan Baker and this is Big Day in Education. Today we're going to continue our discussion of diagnostic metrics for classifiers. As we discussed earlier, different methods require different measures. And today we're going to continue our focus on classifiers. Later in the week we'll discuss regressors, and other methods will get worked in later in the course. Last class, as you may recall, we discussed accuracy and kappa. And today we're going to discuss additional metrics for assessing classifier goodness. The first is the receiver operator characteristic curve. With ROC curves, you're predicting something which has two values. Correct or incorrect is one example, or maybe gaming the system versus not gaming the system, or did the student drop out or not. Your prediction model is outputting a probability or other real value. So instead of just your prediction model saying, yes, this student will drop out, it's saying the student will drop out with 73% probability. And you want to ask the question, how good is your prediction model? Let's look at an example. Let's say that you have the following predictions from your model and the following ground truth. And with an ROC curve, what you do is you take any number, actually you take every number, and use it as a cutoff. Whatever number you choose, some number of predictions, maybe 0, is then going to be classified as 1s, and the rest, again maybe 0, will be classified as 0s. So let's say we take a case where the threshold is 0.5. In that case, 0.7, 0.8, 0.55, 0.51, and 0.95 are going to be classified as 1. You'll notice that that's actually correct in 4 of those cases, but it's wrong in the case of 0.55 where the truth was 0. So if we say our threshold is 0.6, then two of them flip. 0.55 and 0.51, which were previously above 0.5, so they were treated as 1s, are now treated as 0. This actually doesn't make the model any better, because in one case that makes something that was wrong right, and the other case it makes something that was right wrong. 0.55 was previously wrong, now it's right, because now it's below 0.6, so it's 0, which is the truth. And 0.51 was previously above, and it's 1, so that was correct. Now it's below, and that's wrong. So you can see that as we change the thresholds, some of the data points go from being right to wrong in each direction. There are 4 possibilities for any classification threshold. The first is true positive. Both the model and the data say it's 1. Then there's false positive. The data says it's 0, but the model says it's 1. Then there's true negative. Both the data and the model say it's 0. And finally, false negative, where the data says that it's 1, but the model says it's 0. And you'll get a different blend of these 4 possibilities as you change your threshold. So if we have a threshold of 0.6, you can see that 0.1 is predicted to be 0 because it's under 0.6, and the truth is 0, so that's a true negative. 0.7 is predicted to be above 0.6, so it's seen as being true, and it is true, so that's a true positive. You'll note as we go down to 0.51, we have a case where 0.51 is below 0.6, so it's seen as being a 0, but it's actually a 1, and that's a false negative. If we switch to a threshold of 0.5, that 0.51 becomes a true positive, but 0.55, which is now above 0.5 and treated as 1, it's actually 0, becomes a false positive. And again, if we try other thresholds, we'll have a different balance. If we try a threshold of 0.99, that's above all of the predicted values, so in fact everything's going to be treated as 0. Everything will be either true negative or false negative. An ROC curve graphs 2 relations. The first one on the x-axis is the percent false positives versus true negatives. So of the cases then the data are 0, what percentage of them are actually classified correctly by the detector, and which percentage of them are classified incorrectly, meaning false positives. And we put false positives to the right and true negatives to the left. The y-axis graphs the relationship between true positives and false negatives. So of the data that's truly positive, of the data that's 1, what percentage of them do we say that's true positives versus false negatives? And the true positives go up and the false negatives go down. So let's look at an example. We can see the false positive ratios on the x-axis, true positive ratios on the y-axis. So this model for anywhere along the curve is actually got more true positives by a proportion than false positives until we get to the very top corner. Now you might say, what's that dashed line? That dashed line's chance. When your true positive ratio is 50% and your false positive ratio is 50%, or your true positive ratio is 20% and your false positive ratio is 20%. So if your model is performing exactly at chance, getting as many true positives as false positives, then it's going to be right on that dashed line. So the more you are above that dashed line, the better you're doing. So is this a good model or a bad model? This is a chance model. Again, it's right on the dashed line. Now this is a good model. It's one worth looking at. you'll note that it's pretty much well above the diagonal line. But note those stair steps. Those weird little stair steps are kind of indicative that the model has got lumpiness in it, and we'll talk about that later in the class. This is a poor model. It's mostly above the dashed line, but it actually dips below it at one point. You typically don't want a model that does this. Finally, we have a model that's so bad it's good. Who out there has an uncle? An uncle who, whatever they tell you, you know that it's wrong. Like if your uncle says the Democrats are going to win the election, then the Republicans are definitely going to win it. And if he says the stock's going to go down, then you should buy a lot because it's going to go up. Some people are so often wrong that you can kind of just take whatever they say and do the opposite. And that's what this model is here. In practice, you could take this model and say, every time this model says true, say false. And every time this model says false, say true. In practice, you probably don't want to do this though, because usually what this means is your model just didn't work on new data. You want to have a really good reason to believe that the model actually is wrong all the time, like your uncle.
Now, taking an ROC curve, we can compute what's called the AUC ROC, also called AUC sometimes for short, or called A prime, or even called Wilcoxon at times. This is the area under the ROC curve we've just seen. AUC is mathematically equivalent to the Wilcoxon statistic. It's the probability that if a model is given an example from each category, it'll accurately identify which is which. I personally find that a little bit clearer way to think about this. The equivalence to Wilcoxon is useful for another reason, because it means that you can compute statistical tests, first of all, for whether two AUC values are significantly different from each other. That's true on the same data set or even on different data sets, and whether an AUC value is significantly different than chance. I should note, however, that there's not really a good way to compute AUC for 3 or more categories. There are methods, Hand and Till has a paper on this, but the semantics change a little bit. For comparing two models, any two models, what you do is you can compute a z-value based on the AUC of the two and their standard error. You can also use this same set of formulas to compare the model to chance, simply by, instead of having two models AUCs and the standard error of each of those AUCs, taking the AUC and standard error of one of them and 0.5, the chance value, and a standard error of 0 for the other. You can compute the standard error as follows. I won't go through the details on these equations, but feel free to pause here or to look back at the slides later. There is, however, a complication which is worth noting. This test assumes independence. If you have data for multiple students, guess what? Two data points from the same student are not independent of each other. In this case, what you can do is compute AUC and statistical significance for each student and then integrate across the students. Now, there are reasons why you might not want to compute AUC within student. For example, if there's no intra-student variance, if a student's data points are very highly correlated to each other. But if you don't do this kind of separation out, don't do a stat test. If you are not going to separate out by student, if you can just throw it all in a hopper, go ahead and compute AUC, but don't do a stat test on it.
Now, one other note of caution. The implementations of AUC remain buggy in many data mining and statistical packages as of this recording in March 2018. But AUC does work in scikit-learn and Python, and there's a correct package for R called AUC Tester. Not the same as the standard AUC package in R, which does still have bugs, last we saw. If you use other tools other than R or Python, see my webpage for a command-line and GUI implementation of AUC at the link below.
AUC and kappa. Want to make a quick comparison. AUC is more difficult to compute, and it only works for two categories without complicated extensions. But it's got some benefits. First of all, the meaning is invariant across datasets. An AUC of 0.6 is always better than an AUC of 0.55, regardless of your dataset. And it's easy to interpret statistically. You can even do statistical significance tests. AUC values are also almost always higher than kappa values. That's because AUC takes confidence into account and kappa doesn't. Another couple important metrics are precision and recall. Precision is the true positives divided by the true positives plus the false positives. And recall is the true positives over the true positives plus the false negatives. So what do these mean? Well, precision is the probability that a data point classified as true is actually true. So if your model says, this is what I'm looking for, is your model right? Recall says the probability that a data point is actually true is classified as true. So what this means is, if I'm looking for this, what's the probability I'm actually going to find it? Incidentally, for those of you intellectually raised in statistics land, FP, false positive, is what statisticians often refer to as a type 1 error, and FN, false negative, is what statisticians often refer to as a type 2 error. If that terminology is unfamiliar to you, don't worry about it.
Now there's still active debate about these metrics. Jenny and colleagues find evidence that AUC is more robust to skewed distributions than kappa, and also several other metrics. By contrast, Donani et al. Find evidence that models selected with RMSE, which we'll talk about next time, come closer to the true parameter values in simulated data than AUC. A third perspective, Pelinek, argues that AUC only pays attention to relative differences between models and that absolute differences matter too. So there's quite a bit of debate here, and the opinions of the field will probably change again over the next couple years. I'm still a big fan of AUC.
In the next lecture, we'll talk about metrics for regressors. Thank you very much. This is Big Day in Education.